In 2023, astronomers pointed the James Webb Space Telescope at a patch of sky and found galaxies that should not exist. Too massive, too structured, too early. The standard model of cosmology says those galaxies needed billions of years to form, but they appeared in the first few 100 million years after the Big Bang. That discrepancy has a name in the literature. Researchers call it the impossible early galaxy problem, and it is forcing physicists to ask a question they have carefully avoided for a century. What if the Big Bang was not the beginning? That is not a philosophical question anymore. Several independent lines of physics now point toward the same uncomfortable answer. Something came before. This video is about that physics, not the speculation, the actual mathematics, and what it predicts. We will move through three distinct frameworks, each developed by serious physicists, each with its own predictions and its own tensions with observation. But first, what does the Standard Model actually say about t equals 0? The Standard Model of cosmology is built on general relativity and a set of initial conditions we call the Big Bang. The model is extraordinarily successful. It correctly predicts the cosmic microwave background, the abundance of light elements, and the large-scale structure of the universe. But it has a crack at its foundation. When you run general relativity backward to the very beginning, the mathematics breaks. Density becomes infinite. Temperature becomes infinite. The equations produce what mathematicians call a singularity. A singularity is not a physical thing. It is a flag the equations raise to say, we have stopped working. General relativity was never designed to describe quantum scales. And at the very first instant, the universe was quantum, smaller than any particle we know. So the singularity may not be a real physical event. It may simply be the edge of general relativity's competence. That insight is the wedge that three competing frameworks have pushed through. The first is loop quantum cosmology. Loop quantum cosmology, or LQC, was developed primarily by Abhay Ashtekar and his collaborators at Penn State in the early 2000s. It applies the principles of loop quantum gravity to the entire universe, treating space-time itself as made of discrete quantized loops at the Planck scale. The Planck length is 10 to the negative 35 meters. Below that scale, our normal picture of smooth space-time simply has no meaning. In LQC, the singularity dissolves. When you use quantum-corrected equations to run the universe backward, the collapse does not end in a point of infinite density. Instead, quantum repulsion kicks in at the Planck scale and the contraction reverses. The universe bounces. What we call the Big Bang in this model is the Big Bounce, a transition from a prior contracting phase to our current expanding one. There was a universe before ours. It collapsed, and its collapse seeded ours. This is not metaphor. The equations of LQC are fully written out. They generate specific, testable predictions about what signatures the bounce would leave in the cosmic microwave background. Specifically, LQC predicts a suppression of power in the CMB at large angular scales, a quieting of fluctuations at the largest distances we can observe. The Planck satellite did measure an anomalous low-power signal at those exact scales. It is not yet conclusive, but it is consistent. LQC does not ask you to take the pre-bang universe on faith. It says, here is a specific observational signature, go look for it. That is what separates physics from mythology. Now, LQC has an open problem. It does not naturally explain why the bounce produced a universe as large and smooth and flat as ours. Our universe is suspiciously uniform across distances that should never have been in causal contact. That is the flatness and horizon problem, and inflation was invented to solve it. LQC researchers have proposed that the pre-bang phase itself could play the role that inflation plays, spreading and smoothing the universe before the bounce. The debate is ongoing. The second framework comes from one of the most decorated mathematicians alive, Roger Penrose, Nobel laureate, co-author with Hawking of the singularity theorems, and the man who spent the last 2 decades arguing that the universe has a very different shape in time than we think. Penrose's model is called conformal cyclic cosmology, CCC. It begins with a strange but precise observation about the far future of our universe. In the very far future, trillions upon trillions of years from now, all matter will decay. All black holes will evaporate. the universe will contain nothing but photons and gravitons endlessly spreading apart. Here is Penrose's key insight. A universe made only of massless particles has no meaningful concept of time or scale. Massless particles do not experience either, and a universe with no meaningful scale is, in a precise mathematical sense, conformally equivalent to a very small, very hot, very dense universe, which is exactly what the early universe looked like. In CCC, the remote future of one aeon, Penrose's word for one full cosmic cycle, mathematically maps onto the Big Bang of the next, not metaphorically. Through a precise mathematical operation called a conformal rescaling, the geometry of the dying universe literally becomes the geometry of the newborn one. There are an infinite number of aeons, each born from the death of the last. Now, this is falsifiable. If Hawking radiation carries information as black holes evaporate, the death of each aeon should leave faint circular imprints in the CMB of the next. Penrose and his collaborators have claimed to find exactly those rings in Planck and WMAP data, regions of anomalously low temperature variance arranged in concentric circles. Other researchers dispute the statistical significance. Some say the rings are consistent with random noise. The argument is genuinely unsettled. But unsettled is not the same as wrong. It means we need better data. The Simons Observatory and CMB-S4 experiments, coming online now, are designed to push CMB sensitivity far beyond Planck's reach. They may settle the question. This is what makes CCC remarkable. It is an ancient universe theory that has a contemporary, scheduled observational test. The third model is perhaps the most visually foreign of all, and it emerged not from cosmology, but from string theory. It is called the ekpyrotic model. The word comes from the ancient Greek for conflagration, a great fire. Developed by Paul Steinhardt and Neil Turok in 2001, ekpyrosis proposes that our universe is a three-dimensional membrane, a brain floating in a higher dimensional space. There is another brain, parallel to ours, separated by a gap we cannot see or access. For most of cosmic history, the two brains drift apart, but a weak force, possibly related to the scalar fields described in string theory, pulls them slowly back together. After trillions of years, the brains collide. That collision floods both brains with energy. On our brain, it looks like the Big Bang, a sudden, violent, hot beginning, expanding outward from the moment of impact. But there was no singularity. There was no point of infinite density. There was just an impact between two finite objects in a higher dimensional space. Before the collision, both brains existed. Time existed. Structure existed, possibly including the remnants of a previous cycle. Steinhardt later developed this into a fully cyclic version, the cyclic model, where after each bang, the brains drift apart again, and the whole sequence repeats endlessly. The ekpyrotic model offers a solution to the flatness and horizon problems that does not require inflation at all. The brains are naturally smooth and flat before they collide. That is a direct challenge to the inflationary paradigm, one of the pillars of modern cosmology. The ekpyrotic model also makes a specific prediction. It produces no primordial gravitational waves, or produces them at levels far too low to detect. Standard inflation, by contrast, predicts a detectable background of primordial gravitational waves imprinted in the CMB's B-mode polarization. If the Simons Observatory or CMB-S4 finds that signal, ekpyrosis is ruled out. If they don't find it, ekpyrosis survives and inflation faces serious pressure. We are living inside the window where that result could arrive. Now we return to where we began, the James Webb Space Telescope. The anomalous early galaxies JWST is finding are not conclusive evidence for any pre-bang theory. Let's be clear about that. They are, however, evidence that something in the standard model is incomplete. The leading conventional explanation is that some parameter in galaxy formation models is wrong. Star formation was faster than simulations predict. That may well be the answer. But a second possibility, less comfortable, more radical, is that the universe had more time to build those galaxies because the pre-bang phase provided structure. Some cosmologists have now proposed that the seeds of large-scale structure we see today may have originated before the bounce, inherited, not generated. In LQC, quantum fluctuations from the pre-bounce universe can propagate across the bounce and imprint on the structures that later become galaxies. If that is true, JWST is not just taking pictures of distant galaxies. It is reading echoes from before the birth of time as we know it. That is one of the reasons astrophysicists are watching those anomalous galaxy detections with such unusual intensity. There is also the matter of what these models share, and where they agree, the agreement is striking. All three frameworks, LQC, CCC, and ekpyrosis, agree that the singularity is not real. All three replace it with a transition, a physical event, extended in time, connecting a prior state to our current expansion. And all three are, in principle, testable, not through speculation, but through precision measurements of the sky. That is not always true of cosmological theories. It is a mark of how far the field has matured. But here is what we cannot yet know, and this is important to say plainly. Even if the universe did exist in some form before the Big Bang, we cannot directly observe it. The thermal bath of the early universe erased almost all information from what came before. Almost all, not completely. The specific signatures we have described, the CMB anomalies, the B-mode polarization, the power suppression at large scales, are the narrow windows that may have survived. This is the position cosmology finds itself in right now. Not confused, but carefully probing a boundary that was, until recently, considered completely inaccessible. Roger Penrose is in his 90s and still publishing on this. Ashtakar's group is still refining the LQC equations. Steinhardt and Turok continue to develop cyclic cosmology. These are not fringe voices. They are people whose prior work underpins the textbooks every physics student carries today. When they say this singularity is not the beginning, that something existed before, it is worth pausing to understand why. Not to believe them automatically, to understand the argument. Because the universe has never once respected our assumption that it was created for our convenience, that it began at a moment we could point to and say, there, that is where time starts. Every time we have drawn that line, the universe has turned out to be older, stranger, and more continuous than we assumed. The Big Bang may be a chapter heading, not a first page. And the coming years, with JWST continuing its survey, the Simons Observatory coming online, and gravitational wave detectors increasing in sensitivity, may finally tell us what came before. Not through imagination, through measurement. If you want to follow those results as they arrive, subscribing here means you will not miss the update. Every video on this channel starts from a real mission, a real measurement, a real anomaly, not a what if.